Hey there, welcome to week 2, and this is chapter 1, part 2. It's just the second half of chapter 1. And again, this is a supplement to the slides and annotations, not a replacement for them. Okay, I'm going to start right away by sharing my screen. And we will dive right in. All right. So this is week 2, and it's chapter 1, part 2. So last week, the two things that we focused on during lecture were unit conversions within the metric system and significant figures. So we're going to build on those two topics for this week. First of all, let's take a look at some more challenging unit conversions. Okay, first of all, let's look at the idea that let's do between systems, and let's take a look at the idea that maybe we have 176 pounds, and we want to convert that to kilograms. Okay. All right, so what we need now is we need a conversion factor that will take us between systems, because here we have the English or standard system and here we have a metric system. Okay, and so the conversion factor that I'm going to use for this first one is that there are 2.2046 pounds, and LBS is the abbreviation for pounds, in 1 kilogram. Okay, now the other thing I'm going to do before I go on is I'm going to notice that there are 1, 2, 3, 4, 5 sig figs here. So that means that I can only have 5 significant figures in my final answer. All right, so I start here with my given, 176 pounds, and I'll put that over 1, times, now I've got pounds on the top, so I need pounds here, pounds per kilogram, because that's where I'm going with my conversion factor. Once I've put my units in so that they'll cancel, then I'll go ahead and put in my numbers. And so I have 2.2046 pounds per 1 kilogram. So then I take out my calculator, okay, and I type that in. 176 divided by 2.2046. And the answer that my calculator gives me is 79.8330763. And I determined that I can only have 5 significant figures. And in this case, it's easy because the next one here is a 0. And so it's really, really easy to see that we're just going to round that down. So that becomes 79.833 kilograms. Oh, wait a minute. I did that wrong. So when we look here, and sometimes, so it's really, really easy. So this is always the thing, stop and think, well, wait a minute, did I look at the right thing? I've got 5 significant figures here, but look here. Here, I have 1, 2, 3 significant figures. So if you find yourself in this position, this is a good way to notice what we've done. Oh, okay, now I can only have 3 significant figures. And 3 is less than 5. So we still round down, and our final answer needs to be 79.8 kilograms. Okay. So that's a good example of picking the right one for significant figures. Now let's take a look at something more challenging. Now what we're going to do is we're going to say that we have a minivan, and our minivan gets 21.2 miles per gallon. If you see MPG, it stands for miles per gallon, which really what this means is 21.2 miles per 1 gallon. Okay, and that's kind of an average gas mileage for that kind of a vehicle. And we want to know what that is going to be in kilometers per liter. So this one's going to be a little bit trickier. We're going to need more than one conversion factor. So our distance conversion factors here are miles to kilometers. So what we're going to use there, and there's different ones that you could find, but this is the one that I'm going to use right now, and that's that there are 1.6093 kilometers in 1 mile. You could go the other way around and have 1 kilometer per miles, and it'll get you the same answer as long as you have the correct conversion factor. And now the second conversion factor I'm going to have for going from gallons to liters, that's our volume, is here I have that there are 3.7854 liters in 1 gallon. Now, these are the kind of conversion factors that you would be given on a test, okay? You need to know the metric system conversions. And again, you cannot look things up on the test. So make sure that you have that written down from your slides so that you become very accustomed to them, okay? However, on a test, you would be given a system like this that exists between systems. Okay, so now we take our given here, 21.2 miles per 1 gallon. And before I go on, let's go ahead and take a look at our significant figures. These 16093 and 37845 each have 5 significant figures. But let's not wait until the end like we did and find 2 answers. Let's go ahead and come over here and we'll see that our 21.2 has 3 significant figures. That means that our final answer will need to have 3 significant figures. So you can do it at the end like we did the last one, or you can do it at the beginning and determine that early. Now we set up our next one, and we can't go from miles per gallon to kilometers per liter directly. The first thing I'm going to do is I'm going to eliminate my miles, and here I have them on the top, so I'll need them on the bottom, and then I'll put kilometers here. And then during the next one, I need to eliminate my gallons. So because I have it on the bottom in my given, I'll need it on the top here, and liters on the bottom. So now let's just take a quick look at, here's how our miles cancel. And here is how our gallons cancel. And what you'll see in the end is here we have kilometers per liter, which is what we want our answer to be in for our units. So now we can fill in our conversion factors. And using the first one, we can see that we have 1.6093 kilometers per 1 mile. And here we have 1 gallon per 3.7845 liters. And now we're ready to do our calculation. So I start out by saying 21.2 times 1.6093, and then I divide that by 3.7845. And the answer that my calculator gives me is 9.014971.1595. Now, I determined at the beginning that I can only have 3 significant figures, so that'll be right here. And actually, we have a 4 here, which means that this will also round down rather than up. So my final answer is 9.01 kilometers per liter. And that's an example of a more complicated conversion problem. Now let's take a look at a new system that we want to convert, and that is temperature. There are three scales that are commonly used for temperature. One is Celsius, referred to in degrees Celsius. One is Fahrenheit, referred to in degrees Fahrenheit. And the last one is Kelvin. And those are just referred to as kelvins, no degree symbol. Celsius is metric. Fahrenheit is our English or our standard system that we use here. We're not going to use Fahrenheit in our calculations because it's not considered part of our metric system. And so whenever we're doing a temperature calculation, anything in Fahrenheit would need to be converted to something else in order to do the calculations. Kelvins are also part of the metric system, and they're exactly the same size as the Celsius temperature scale, except for the fact that they're adjusted for absolute zero, which means that there are no negative numbers in our Kelvin scale. And that's very, very important because there will be many times that we're doing calculations and we can't have a scale that doesn't begin at zero, which is why we'll work with the Kelvin temperature scale a tremendous amount in chapter 5. All right, so let's take a look at how we will convert between those. And this is gonna look a little bit different from the way it is in the slides, just to make it simpler. Okay, so first of all, let's say that we're going from Celsius to kelvins. So if we're looking for kelvins, we take our Celsius temperature and we add 273.15 to it. That's because negative 273.15 degrees Celsius is absolute zero, or 0 kelvins. And then of course, if we were to turn it around, and let's say that we want to go from Kelvin to Celsius, we would use this, our Kelvin temperature minus 273.15. Now let's say that we want to go between Celsius and Fahrenheit. So there are equations that go between Celsius and Kelvin and Celsius and Fahrenheit. So if you want to go from Fahrenheit to Kelvin, you have to stop at Celsius first. Okay, so, excuse me. Let's say that we want to go from degrees Fahrenheit to degrees Celsius. Okay, that means that Celsius is our answer. And what we're going to do then is we're going to say, we're going to take our Fahrenheit, we're going to actually, I'm going to write it like this. 5/9 times our Fahrenheit temperature minus 32. And this is a little easier to see, I think, than what is in the slides, unless I've edited the slides since then. I don't have a new copy of them here. Now, if we want to go from Celsius to Fahrenheit, what we'll have is we'll have 9/5 times our Celsius temperature plus 32. So let's take a look at what this would end up being. We're going to say that, and because it's very cold out today, it is a high right now of about 31 degrees Fahrenheit. And I want to know what is that in degrees Celsius and what is that in Kelvin temperatures. So I'll start off by finding my Celsius temperature before I convert to Kelvin. Okay, and so I use the formula that degrees Celsius is equal to my Fahrenheit temperature, 31 degrees Fahrenheit, minus 32, okay, and all that times 5/9. And so I start with 31 minus 32, and it gives me -1, okay, times 5 divided by 9. And this gives me a Celsius temperature of 0.55555, repeating, okay? Now I take a look and I can see I only have two significant figures. So that means that I have to round this up because 5 rounds up. So I have 0.56 with a negative, can't make sure that we don't drop our negative, negative 0.56 degrees Celsius. Okay. Now, in order to go from Celsius to Kelvins, remember that our Kelvin temperature is our Celsius temperature plus 273.15. Now, because this is adding and subtracting, I'm going to line these up so that I can see where my lowest decimal point lies. In this case, it sort of works out quite well. So I have my Celsius temperature, negative 0.56 plus 273.15. All right, well, that's how this is, but I don't like how that's written. So I'm just going to turn it around so that I can actually do this problem by hand. 273.15 minus 0.56. Okay. And so then I can see, yeah, I will actually do the whole thing by hand. Why not? Okay, so I will borrow, and that becomes a 2, a 10, and a 15. Okay, so now I have 15 minus 6 is 9, 10 minus 5 is 5, put in my decimal point, and I have 2, 7, and 2. Now, remember our rules for adding and subtracting say our least number of decimal places, which means that we would keep all of this. And I would just put in my Kelvin temperature like that. Okay. And there are my two answers for this conversion. The next math concept that sort of finishes out this chapter is the idea of density. Density is very important. It is it is one of the primary physical factors that we can use to classify solids, gases, and liquids. Okay, so density is equal to mass divided by volume. Okay, when we are working with solids, we will usually report our density in terms of grams per centimeter cubed. When we are dealing with liquids, we will usually report our density as grams per milliliter. And when we are dealing with gases, in chapter 5 primarily, we will actually be dealing with units of grams per liter. Now, here's an interesting aside, is that 1 cubic centimeter or 1 centimeter cubed is the same as 1 milliliter. So that'll be very important when we're doing water displacement between solids and liquids. And what I mean by 1 centimeter cubed is a small box like this, that is 1 centimeter by 1 centimeter by 1 centimeter. Okay, so let's do a very simple density problem. But before we do that, actually, I want to turn this around because I know that it's been quite a long time since some of you have had a lot of math. So I'm going to go through this section kind of slowly. Now, if density is equal to mass divided by volume, if we wanted to solve for mass, then our mass would be equal to our density times our volume. And if we wanted to solve for volume, then our volume would be equal to our mass divided by our density. So let's do a really, really simple problem here. Let's say that we have an unknown, and our unknown is 11.2 grams. and for a mass, and our volume is 3.6 centimeters cubed. And we want to know what our density is. Okay, so we just say density is equal to then 11.2 grams per 3.6 centimeters cubed. And so we divide that 11.2 divided by 3.6, and we get 3.111111, and so on. However, if we look at our significant figures, we can see that we can only have 2 of them. And 1 rounds down, so this becomes 3.1 grams per centimeter cubed. Okay. Let's remember that, and we're going to use it on the next slide. Now, we're looking at our unknown, and that had a density of 3.1 grams per centimeter cubed. Now, let's say that we have an irregular piece of our unknown here, and we find that it has a mass of 25 grams. And we want to know what its volume is. Well, then we can just solve for volume. And since density is equal to mass over volume, then volume is equal to mass divided by density. Okay, so we have 3.1 grams, we have 25 grams divided by 3.1 grams per centimeter cubed. And that eliminates our grams, and then our centimeter cubed is our answer. So we have 25 divided by 3.1. And this gives us 8.064516. And now, though, we can only have 2 significant figures. See how we have 2 here and 2 here? But now there's a 6 there, and that means that we have to round that up. So our final answer is going to be 8.1 centimeters cubed. Now I want to show you what happens for a couple of other things. Let's take a look at volume. And this is just a little bit of a review. Some important things to know are the volume of a rectangular solid, okay? And a rectangular solid might be something like a fish tank or a box of books. So here's a rectangular solid. And the dimensions that we're going to work with there is we have length, and we have width, and we have height. Okay? And we're going to find the volume of our object in length times width times height. Okay, so, but now what happens if they're not the same? Let's say that our length is equal to 1.5 meters. And our width is equal to 302 centimeters. And our height is equal to, oh wait, that doesn't make any sense. Hang on, we're gonna say 30.2 centimeters. And our height, we're going to say, is equal to 178 millimeters. Now you'll notice here that what I've done is I've given this in 3 different things, okay? And in order to do length times width times height, what we're going to need is we're going to need all of our units to agree. Okay, and let's say that what we want is, our question is, what is our volume in cubic centimeters? Okay, so step one is to convert all units to centimeters. Okay, and that's because we have cubic centimeters, and a cubic centimeter is a centimeter times a centimeter times a centimeter. Okay, so we need to start with that. So now let's take a look here. And first of all, this is already in centimeters, the 30.2, so we don't have to do anything with that one. Now let's take a look at our length. So I'm going to come right here and I'm going to do it in place. And I have 100 centimeters per 1 meter. So I can multiply this. I have 1.5 times 100, and that gives me 150 centimeters. Now this is two significant figures, and this is also two significant figures, because remember, our trailing zero doesn't count if we don't have a decimal point. Okay. And now we have 178 millimeters, but I don't have a conversion that'll get me from millimeters to centimeters. I could. Well, why don't we go ahead and do that? If you were to look at a ruler, you would see that there are 10 little marks between your millimeters and your centimeters. So I would say, oh, well, I know that those 10 little marks mean that there are 10 centimeters in 10, sometimes it is hard to talk and write at the same time, but there are 10 millimeters in 1 centimeter. Okay, so that means that there are 17.8 centimeters here. Our step 2 is to do our calculation for length times width times height. Length times width times height. Okay, so that's going to be 150 times 30.2 times 17.8. And I will do that on my calculator, 150 times 30.2 times 17.8. And the answer that I get on my calculator is 80634. 80,634 cubic centimeters. What a lovely large number. But I have a problem. And my problem is that I can only have 2 significant figures because of this 1.5. The 6 will round up. So there are 2 ways of writing this. I can write 81,000 cubic centimeters, or I can write 8.1 times 10 to the 4th cubic centimeters. I am perfectly fine with both of these answers on a test. Okay, sometimes on a test, there will be an answer already in place that the computer will grade. If you put in, if the computer is looking for 81,000 and you put in 8.1 times 10 to the 4th and it auto grades you as incorrect, do not worry, because I will be looking very carefully at all of your tests and I will instantly see, oh, they answered 8.1 times 10 to the 4th, and I know that that is equivalent to 81,000, and you will not lose any points at all on it. So this is a good place to mention, don't worry at all about the autocorrect grade that Brightspace will give you as soon as you're done with your test. It has absolutely no bearing at all on your final answer. It doesn't even imply how close you were on the auto-graded questions, because I will be going over all of them. Okay, all right, so that is one review for volume. Let's take a look at another review for volume, and that is the volume of a sphere. So a sphere might be a ball, okay? you know, a basketball or a baseball or something like that, a little ball for your dog if you are like me and you have a little dog running around. But it could also be the volume of a star, because for the most part, we will think about stars as spheres, okay? It might also be the volume of an atom, okay? It might be the volume of a proton or the volume of a neutron or the volume of an electron. So if I ever ask for any of these in volumetric form, I want you to use the formula for the volume of a sphere. Okay, and that equation is 4/3 pi r cubed. So let's say that we are, let's see. Sometimes when I'm coming up with things because I haven't planned well enough, I just have to come up with an idea. All right, well, let's say that we have a ball and our ball has a diameter, I'm imagining, of 12.48 centimeters. Okay, so here is my original value. And that has 1, 2, 3, 4 significant figures in it. So we're going to remember that. And I want to know what the volume of my ball is. So my step 1 in this case is that I need a radius. Okay, so remember that if you have a circle, your diameter is all the way across, and your radius is half of that. So the radius is equal to 1/2 of the diameter. Or 12.48 divided by 2. So I get 6.24. However, I have to remember that I actually have 4 significant figures here, and here I've only written 3. I am confident this much because of my significant figures, okay? And 6.24 versus 6.240 isn't different as far as numbers go, it's just different as far as our confidence goes. All right, so then our step 2 is to find the volume of our ball, and that is going to be 4/3 times pi times our radius cubed, 6.240. Okay, now every calculator does this a little differently. I highly encourage you to grab yours. If you need to, pause the video right now and see and work through it on your own, or work through it while I am working through it, but make sure that you're typing this into your calculator correctly. On my calculator, I will do 6.240 and I will cube that. And then I will multiply that by 4 and divide it by 3. And then I will multiply it by pi. And the answer that I will get on my calculator is 1017.75297. But I can't use all of those. I can only have 4 significant figures, 1, 2, 3, 4. And the 7 means that I will round up. So the volume will be 1,018 cubic centimeters. Okay. if you had used 3.14 instead of the pi button, this would have actually come out as 1017. So just to warn you, there's that tiniest bit of error if you don't use the pi button. It's a pretty small value though, okay? So that is how we would find the volume of our ball. Now let's say that our ball is made of, I don't have densities in front of me. Okay, so we won't work through that more, but that is how you do that. And we will be working more of these problems in recitation as well. All right, excellent. That is pretty much the end of the math that we'll be doing. I want to give you just a little bit of a review. This is in the slides and in the annotations, but let's just take a look a little bit for a few minutes about our organization of matter, okay? And I will not be covering everything in the slides. So again, make sure that you are checking out the slides. Matter is broken up into some different categories, okay? So let's say that we can have a couple of different things. One is matter can be in mixtures, or it can be in pure substances. Mixtures occur when we have a variety of things that are not chemically combined. So examples of that might be things like air, dirt, you know, a box of Legos. You have a bunch of things in it and they have all those pieces, okay? Pure substances are chemically combined and they're all the same throughout. Now, pure substances come in two different varieties, okay? And it's going to look a little bit different here. They can be in compounds, or they can be as elements. Elements are things that we will find on the periodic table, okay? And there's a and you can see that it's one of the attachments in this week. Okay, it's also in week 3 because that's when we'll really be using them. But you won't be using it a lot in this chapter, but you'll be using it a lot in chapter 2. Okay, but make sure that you take a look at the periodic table. And some examples of elements might be carbon. And its symbol is a C. Another example might be hydrogen. Now, hydrogen is a diatomic gas. Its symbol is an H, but it can also be written as H2. Okay, and that's because hydrogen doesn't exist in nature as just one H. I'm just going to neaten that up a bit. Okay, some other examples of that might be gold. I changed color, didn't intend to do that. The symbol for gold is AU. So you'll notice that for all of these, we either have one letter or we have two letters. And the first letter is a capital and the second one is a lowercase. Or we have a single letter with a 2 after it to indicate that it's diatomic in nature. Okay, some example of compounds might be water. Water is H2O. You see how both of these are capital letters? That indicates that it's two different elements chemically combined to form our compound. Another one might be methane. Methane is CH4, 1 carbon chemically bonded to 4 hydrogens. And we will be working between elements and carbons a lot, okay? Elements can exist by themselves, but they also make up all of our compounds. So compounds are made up of elements. There are 2 different types of mixtures now. There are homogeneous mixtures, and there are heterogeneous mixtures. This is a place where understanding where word roots is very, very important. So where word roots come from, sorry, like our Latin roots or our Greek roots. So if you understand those roots, you know that the root homo means same and hetero means different. Now, what that basically is talking about is that in heterogeneous mixtures, you can see visibly distinguishable things. So an example of a heterogeneous mixture might be a box of Legos. I have kids, so we have boxes of Legos. We also have entire floors covered in Legos. But that's a good example of a heterogeneous mixture because I can see all those pieces of Legos. Now, maybe one of my boys has made a Lego spaceship, which they like to do. That Lego spaceship is a great example of a mixture. The Legos aren't combined chemically, they're just stuck together. And it's a mixture of different Legos. And we can see each and every Lego in that spaceship. And so that's a heterogeneous mixture. A homogeneous mixture is one where we can not see visibly distinguishable parts. So a great example of a homogeneous mixture might be something like tap water. So when you turn on your faucet, it looks like pure water, but it's not. There's all kinds of things mixed into that water from the treatment that it's coming from. Humans actually don't drink pure distilled water. We actually need water with all of our little stuff in it. So that's really important. So if you are given tap water is going to be a homogeneous mixture. Pure water is going to be a compound because it's chemically combined, but tap water has all kinds of other stuff in it. Seawater, let's say ocean water, let's say we go to the beach and we take a bucket and we scoop up some water. Well, then you're going to be able to see all kinds of things in it. You're going to be able to see sand floating in it, and you're going to be able to see little bits of seaweed floating in it, and there might be little rocks sinking to the bottom. So seawater or ocean water is mostly going to be a heterogeneous mixture. Like let's say we've gotten a bucket of it at the ocean, not necessarily that we've gone out to the middle of the sea and pulled up a perfect, sample of seawater where we can't see anything. Or a homogeneous mixture would be something like tap water or that ocean water that we get out in the center of the ocean where we know that we're getting just water because we don't have sand and all kinds of other stuff necessarily mixed into it. And then pure water is a compound. Okay. The last thing that I'll go ahead and talk about here are some separation means. So we have 2 different kinds of chemical reaction, or actually changes in general. So let's just not think about them in terms of chemical reactions just yet. Let's think of them in terms of changes. Because whenever we're studying chemistry, really what we're looking at is change. We might look at systems as they are, just a static system, but that's not as interesting as a system that's changing. So let's think about a couple of different changes. We have physical changes, and we have chemical changes. Okay, now this is very complicated. Mainly because in my experience when I'm tutoring high school students, sometimes or with students who have come out of high school chemistry, they will come with the idea that a physical change is reversible and a chemical change is not reversible. And I am here to tell you that that is absolutely not the right definition at all. Do not use that one. There are many physical changes that are not reversible, okay? Or at least not easily reversible. A good example of that would be breaking an egg, okay? If you take an egg and you break it and you drop it out, you have just done a physical change. You've broken that eggshell. You cannot simply put the egg back into it. So that's a good example of a physical change that is not reversible. Another physical change that is not easily reversible is, let's say that you are making masks, like many of us, right? And so you are cutting fabric. If you cut a piece of fabric, you cannot simply stick it back together again and have it be exactly as it was before. So that's another example of something that is not reversible, but is only a physical change. So what is a physical change? A physical change is a change that doesn't change the chemical composition. So the examples that I had given before were things like cutting a piece of fabric or breaking an egg. Some other examples of physical changes are state changes. So let's say that you take some water and you freeze it and you make ice, or you take your ice cube and you melt it to make water. We haven't changed the water at all. We've just sort of changed how it's stuck together. So that's another example of a physical change, okay? So physical changes are changes that do not change the chemical composition. Chemical changes are changes that alter the chemical makeup of what we're doing. So for example, here we were cutting fabric, but let's say that we burn that fabric, okay? And whenever we're burning something, it mixes with oxygen. So whenever we're burning something, that's always going to be a chemical change. It changes what we have. So you could imagine that you're having a campfire outside and you're burning wood. Well, so cutting the wood into pieces is a physical change, but burning the wood in your campfire is a chemical change. Some other examples of that for a physical change might be while you're stirring your ingredients together to bake cookies. Let's say that you put your flour and your sugar and your spices and some oatmeal, some oats into a bowl and you stir them together. Stirring them together is a physical change, making mixtures. Now you add in your leavening agents and your liquids, you mix them together and you put them in the oven and you bake them. Baking those cookies is a chemical change. So a chemical change does change our chemical composition. So you might be saying, well, wait a minute, but you said that those were sometimes reversible. And the examples I gave you were not. And that's true. Burning wood in a campfire or baking cookies is irreversible. It's not something that we can just send back the other direction. But there are a lot of chemical changes. For example, making water. You can take hydrogen and oxygen and give them a spark, a little bit of flame, and make water. However, you can also take water, apply an electric current, and separate it into hydrogen and oxygen. I'm just going to balance this. And you don't have to worry about that just yet because we won't be balancing chemical equations until chapter 3. But those are some examples of physical changes and chemical changes. All right. I look forward to seeing you all in recitation. Bye.